Math 3, Unit 7, Module 3, Topic 2, Lesson 3, Inverses of Exponential Functions. Consider the table and graph for the basic exponential function f of x equals 2 to the x and its inverse. Fill in the key characteristics in the table below. So for the domain for f of x, it's going to be negative infinity, comma, infinity, because this keeps going forever to the left. This keeps going up and right forever and ever and ever. So all the x values work. Domain is all your x values. For the inverse function, you'll notice that it looks like this graph is going to keep going down forever and ever and ever, but it's never going to cross over the y-axis. So we're not going to have any negative x values. So we're going to go with 0, comma, infinity. Because again, x isn't going to be 0 or anything negative. So 0 to infinity for the domain of the inverse. For the range of the original function, the range is all your y values. So we're never going to touch the x-axis. So 0 all the way up to infinity, because we're going to have only positive y values. For the range for the inverse, it looks, it's going to go down forever and it's going to go up forever. So it's actually going to be all real numbers. So negative infinity, comma, infinity for the range for the inverse, because it just keeps going forever up and down. So here and here. For the asymptotes for the original function, we're never going to hit the x-axis, and the x-axis has an equation of y equals 0. So there's going to be a horizontal asymptote at y equals 0. For the inverse, you're never going to touch the y-axis, so the asymptote is going to be a vertical asymptote at x equals 0. The x-intercept for f of x, well, there is no x-intercept because you're never going to hit the x-axis. So we would just say none. And then for the inverse, the x-intercept is right here at 1, comma, 0. For the y-intercept for the original function, we're right here at 0, comma, 1. And then for the inverse, there should be no y-intercept because we never touch the y-axis, so we'll write none. For intervals of increase and decrease, looks like both functions are going to be increasing the whole time, because as you look at the curves from left to right, they're always increasing, they're always going up. So I'm going to circle the word increase, and the original function is increasing across its entire domain, and its domain was negative infinity to positive infinity, so that's the interval where it's increasing. For the inverse, it's increasing across its entire domain, and its domain was only 0 to infinity. And then for end behavior, as x approaches infinity, f of x approaches infinity. So we're looking over here. So as x gets bigger and bigger and bigger, your y values go up. They get closer and closer to infinity. And then as x approaches negative infinity, f of x approaches 0. So as your x values are getting smaller and smaller and smaller, we're looking right here, this curve keeps getting closer and closer and closer to 0. For the inverse, as x approaches infinity, f inverse of x approaches. So we're looking here, as x is getting bigger and bigger and bigger, we're going to approach infinity. And then as x approaches 0 from the right, so that little plus sign means that I'm approaching 0 from the right, then f inverse of x approaches negative infinity. So as my x values get closer and closer and closer to 0 from the right side of the equation, my y values get closer and closer and closer to negative infinity. I don't know why I put that little half. There we go. Get rid of that parentheses at the end there. So those are your key characteristics of the original function 2 to the x, and then its inverse function. So this section is about logarithms. The logarithm of a number is the exponent to which the given base must be raised in order to produce the number. If y equals b to the x, then x is the logarithm and can be written as log base b of y equals x. The value of the base of a logarithm is the same as the base in the exponential expression b to the x. So you can kind of match up the different pieces over here. So the base b is the base of the logarithm, and then the exponent x is the answer, and then the y is the part right there in parentheses. It all kind of matches up. So as far as some restrictions on different variables, you could just read those in the table right there. And then let's get a little bit of practice with rewriting exponential form to logarithmic form. So in this table here, in the worked example on the right, they give us all sorts of examples. So that first example A, y equals b to the x is the same as log base by equals x. That second one, we know that 16 is equal to 4 squared. We can write an exponential equation as a logarithm. So the base of the exponential form, the 4, becomes the base of the logarithm. So that little tiny 4 under the word log. The answer, the 16, becomes the part after the word log. And then the 2, the exponent on the number in the exponential form, becomes the answer of the logarithm. So again, if I kind of highlight or color code this a little bit, the 4, oh, that did not work. The 4 matches up with the base 4. The 16 matches up with this 16. And then the square, the 2, matches up there. So as you look at all of these, the base becomes the base of the log. So 10 is the base, it becomes the base of the log. And then the answer becomes the part after the word log. And then the exponent becomes the answer after the equal sign in the logarithmic form. So that is how you go back and forth between exponential form and logarithmic form. So over on number 1, why don't you pause the video and try to rewrite those logarithms as exponentials. Now that you have hopefully tried that, when I try to write log base 10 of 1,000 equals x as a exponential form, the 10 is the base, the x is the exponent, and then the 1,000 would be the answer. For part B, I have a 5 as a base, the other 5 as the exponent, and then the x as the answer. On that last one, the x is the base of the exponent, the 1 is the exponent, the 9 is the answer. For number 2, the graph of h of x equals b to the x is shown. Sketch the graph of the inverse of h of x on the same coordinate plane. Label coordinates of points on the inverse of h of x. So we had learned a long time ago that whenever you're doing an inverse of a function, you just switch the x and y coordinates. So instead of having x, y, you literally just switch the x and y coordinates like that. So with all of these points that they gave us, I'm just going to switch the x's and the y's. As far as the visual goes for the graph, whenever we have an inverse, it's always taking the original graph and reflecting it over the line y equals x. So if I try to sketch in y equals x right here, all the points that are currently plotted, I want to just flip them over that purple line that I drew in. So obviously it's hard to be perfectly accurate, but I'll do the best I can. So that first one, I'm going to put about here-ish. So that would be 1 over b squared, comma, negative 2. So I just switched the x and the y. And then the next point, when I flip it over the axis, it'll be about here. And that'll be 1 over b, comma, negative 1. Again, I'm just flipping the x and y coordinate. That next point was 0, 1, so now I want 1, comma, 0. 1, comma, 0. And then the next point was 1, comma, b, so I'll do b, comma, 1. So about b, comma, 1. And then the next point was 2, comma, b squared. So I'm going to do b squared, comma, 2. Just switching the x and the y. And then that last one, I think that's it. And then I draw my curve. It looks something like this. And I want to label that as the inverse. So h inverse x. Down on number 3, they want us to write the equation of the inverse of h of x equals b to the x. So normally when we do inverses and we're given an equation, we let, h of x or f of x or g of x or whatever it is, we let that equal y. And then we normally switch the x and the y like that. So then from here, what I want us to do is we want to use the properties of logarithms, and we want to rewrite this exponential form into logarithmic form. So I'm taking this equation in red and I'm just rewriting it as a logarithm. So log, and then I take the base, so b is the base, and then the x is there, and then the y is there. Meaning the inverse of h of x, if I just rewrite it with the proper notation, so the inverse h of x, inverse h of x, is going to be equal to log base b of x. Had a feeling that was going to happen. Like that. And then they want us to label on the graph too. So up here I'm going to put log base b of x. So what we're trying to get out of this fact is that an exponential function's inverse is going to be a logarithm. Again, the big thing to get out of this is that an exponential function's inverse is going to be a logarithm. So the final answer over here in the corner is this. A common logarithm is a logarithm with base 10 and is usually written without a specified base. So basically this 10 right here got dropped in this version. And then a natural logarithm is a logarithm with base e and is usually written as ln. So the e gets dropped and then the word log changes to the letters ln. So that's, you say natural logarithm or natural log when you do that. For number 4, they already graphed p of x and q of x for us. And then we're going to sketch and label the functions c of x equals log of x and n of x equals natural log of x. So basically, we're supposed to think about the bases that we don't actually see there. So when it says log of x, there's technically the invisible 10 there that we just don't write. And then when it says natural log of x, there's technically the base of e there that we just don't write. So when we look at the graphs that are already graphed for us, the base of 3 is the function right here. So if I have a base of 10, I want that to be even closer to the x-axis. So let me change my colors, and I'm going to put my dot here at 1, 0 because that point is on every single logarithm. So then I'm just going to sketch this the best I can. Sorry, it gets a little hard to see there. So that would be n of x equals log of x, because there's that base of a 10 there. And then as far as the natural log, since that base is e is approximately 2.7. So since 2.7 is in between 2 and 3, I want to draw this curve in between the two logs that they started us off with. But since 2.7 is way, way, way closer to 3, I want to make sure that my curve is way, way closer to the log base 3 of x. So basically, I'm just going to try to shove this in a little lower than that. Let me try again. Right about there. And it's still going to go through 0, 1. And I'll just go like this so we can actually see it. So that would be n of x equals natural log x. And I see I accidentally named my other function incorrectly. So if you look back on the red label, I put n of x. That should actually say c of x. So let me fix that. That should be c of x equals log of x. On part B, what is the inverse of the logarithmic function c of x equals log of x? So if they want me to do an inverse, like we talked about before, we want to switch the x and the y. So I'm going to let c of x be y, and then I'm going to switch my x and my y, and then I'm supposed to solve for y or get y all by itself. So in order to do that, I'm just going to rewrite that logarithm into exponential form. So I'm going to put in the little invisible 10 as the base. And then again, I'm just going to rewrite this as exponential form. So the base 10 becomes the base of the exponent. The y becomes the exponent. And then the x should just stay like that. And I feel like I did something wrong. Hold on 1 second. Yes, I did do something wrong. Back that up a second. I had my x and my y switched. So the base is the 10. The y goes here and the x goes here. Yes, that's better. So y equals 10 to the x. That is going to be our inverse. And if I want to have the correct notation, I would do c inverse x equals 10 to the x. So this part highlighted in green, that would be our final inverse. On part C, we would want to switch the x and y to start. So let n of x be y, like we always say. Switch x and y, and then we would essentially solve for y. I'm going to put in our invisible base, the e, because that's the base of the natural log. That little ln is the natural log. And then I'm just going to rewrite this in exponential form. So I'm basically solving for y. So the e is the base, the x is the exponent, and then the y is the answer, like that. So y equals e to the x. And then if I'm using the right notation, I would say n inverse x, or the inverse function, equals e to the x. So this part highlighted in green would be our inverse of n of x. And at the end here, we're going to not scroll so far. We're going to identify the key characteristics for exponential and logarithmic functions to complete the table. So we're basically saying for all exponential functions and then for all logarithmic functions. So the visual that we're getting is right, if I scroll back, basically these visuals right here. So the one I'm about to highlight in green, this one, this is your basic exponential that we're going to be basing everything off of. And then the one in red is your basic logarithm. So if I slide back down here so that we don't have to keep sliding back and forth and back and forth and back and forth, let me do the graphs. And I actually put a spot for us to do the graph anyway. So let's just put it in here so we don't have to worry about it. So our function for basic exponential function, let's just say f of x equals b to the x. And then for the logarithm, we'll say g of x equals log base b of x. So those would be inverses of each other. So our basic graph for an exponential would be, let me put my x and y in here. It would be something like this. And then my basic graph for a logarithm would be something like this. So our domain is negative infinity to infinity. Our domain for the logarithm would be 0, infinity. Our range for the exponential function would be 0, infinity, because we don't have any negative y values. And then our range for the logarithm would be negative infinity to infinity, because all the y values work. For the intercepts, for the basic exponential function, you have an intercept right here at 0, 1. And then for the logarithm, you have an intercept right here at 1, 0. For asymptotes, we have a horizontal asymptote at y equals 0. So basically right here, horizontal asymptote at y equals 0. And then for the logarithm, vertical asymptote right here at x equals 0. And then for end behavior, as x approaches infinity, f of x approaches infinity, because it keeps going up forever and ever and ever. And then as x gets smaller and smaller and smaller, as it approaches negative infinity, f of x, our y values, get closer and closer and closer to 0. For the end behavior for the logarithmic function, as x approaches infinity, g of x, or our output values, get closer and closer and closer to infinity. And then as x approaches 0 from the right side, so I put a little plus sign to represent approaching 0 from the right side, then g of x, our y values, get smaller and smaller and smaller. They approach negative infinity. Now this lesson is definitely a little tricky. I'll give you a practice worksheet to work on tomorrow. And then basically just go back and kind of replay this and pause it when you get confused. And again, you'll have practice on it tomorrow, because I know this is definitely kind of tricky. Thanks for hanging in there.